very much all of those people who have stuck with us. I think we're still at around about 75 odd. So the next technology that we're going to look at is range extended technology, and I'm very pleased that Richard Lidston Scott from Teva is here to give us the results of their program. Richard.
Okay, hello everybody. I'll not turn my video on because although I've put my best working from home pajamas on, that's not something that anybody needs to see. So if you'd like to go on to the next slide for me, please, Andy. So the summary of this project is that we've taken, with UPS, 15 of their PAT delivery cars, as they call them. These are based on 7.5-ton Mercedes Vario trucks that, as I'm sure you all know, have been out of production for a while now, and only reach the Euro 5 emission level. So the objectives of the trial were to build 15 of these, at the same time as completing the development of a new battery pack that was compatible with a range of 7.5-ton and upwards commercial vehicles, plus an in-service range of 100 kilometers, and reduce the mass of the original prototype that we gave them by circa 300 kilos. What we managed to deliver was 13 vehicles. We did actually deliver 15, but because of the timing, Innovate felt they couldn't support the last two, so only 13 got funded, but 15 are still in service today and will remain in service with UPS for the next 8 years. I think is the life they've planned for them. So they are electric diesel series hybrid trucks, which means they're all electric drive all of the time, and the 1.6 diesel engine that we swapped the original 4.2 litre diesel engine for is only there to act as a backup generator. Typically, these vehicles trunk in from the UPS depots of Southampton and Tamworth. Tamworth is probably the most interesting duty cycle because it's high-speed motorway trunking for the first 20 miles, then it's super high-density urban delivery for the next 8 hours, and then it's a quick thrash back to the depot at the end of the day. Whereas Southampton, it's far shorter mileages, and the trucks pretty much spend the entire time all electric. UPS typically run out of volume before they run out of gross vehicle weight allowance. So even though we've probably stolen in the region of 500 kilos from the payload, it doesn't actually impact the operation of the vehicle. From a charging point of view, it's very simple for the UPS and operators to adopt this technology. We have a charger fitted to the vehicle, so all you need to do depot side is supply an interface box to the standard 3-phase industrial supply. The aim is that a series hybrid vehicle like this means that you can do the same duty cycle as the base vehicle. So other than plugging it in at the end of the night, there are no additional operational impacts. If you could move on to the next slide, please, Andy. Thank you. So how did we do? From an operational point of view, not bad. The base Euro 5 vehicles are doing 14-15 litres per 100 kilometres. I can't do that in miles per gallon off the top of my head, I'm afraid. And the series hybrid vehicles that we built were averaging over the trial 0.62 kilowatts per kilometre of energy charged. What is interesting that both myself and Teva's sales director David Thackeray can drive a 7.5 tonne at probably 0.3 to 0.4 kilowatts per kilowatt hours per kilometre. So driver behaviour does have a huge impact on the energy consumption. We travelled nearly 64,500 kilometres. We were late getting the vehicles into service, so we haven't covered the mileage we hoped we would, but that's what happens when you try and accelerate a development vehicle in the 2-year time frame of a trial like this. So nearly 50,000 kilowatt hours of energy to be used, and of that 50,000 kilowatts, nearly 10,000 actually came from regenerative braking. We've wound the regen braking up on these vehicles as far as it can go. You can drive one of these vehicles pretty much all day without using the brakes, unless you need to actually stop at a junction or lassie runs out in front of the vehicle. So during the pilot, we did prove that these vehicles can do exactly the same operational duty cycle as a base diesel truck, with the advantages of an EV, but with the range capability of a diesel. So here's an example of a typical day. Is there a pointer function on this, Andy? Oh, if there is, I don't know how to control it. Never mind. So what happens is at point 1, the vehicle is at the depot. It leaves the depot. It's fully charged. It runs out through this blue zone, which is a pre-charge zone. So it will run the range extender automatically to keep the battery topped up on its way into Birmingham. At point 2, it knows it can switch off. So it's running pure EV. And it can keep, sorry, it's still running at this point. So by the time it gets into its drop zone, point 4, it's still basically a fully charged EV. At which point it goes on to all EV operation. It spends the rest of the day. Now, typically, believe it or not, this is 8 hours worth of traveling. The driver finishes his duty, his operational drops. He's normally doing about 120 drops a day, comes out, batteries at 35%. Typically that would be not enough battery to get back to base. So let itself run down to 25%, and then it will kick back in again to the range extender will kick back in again to maintain that 25% state of charge until it gets to what we call the final depletion zone, which is a radius around the vehicle's base. And once it passes the threshold of that radius, for every 800 meters as the crow flies, it gets closer to base, it will allow the vehicle state of charge to drop by an additional 1%. What this means is we are sweating this battery as far as it can go. Now, we only take the battery down to 10% because we don't want to damage it. These batteries are spec'd to 2,000 cycles, which is equivalent to 7 to 10 years in service. But if you run them down below 10% every day, you are going to impact that lifespan. So you can see here, the vehicle's done 115 kilometers. It's used 90% of its battery. It's used about 1.2 litres of fuel. If there are any questions about that slide, I can take them later. Over to you, Brian.
Brian, I think you might be muted still.
Well spotted, Andy. Thank you. Yes. Yes. So as with a plug-in hybrid car, for example, if any of you have got one of those, the same applies with this range extended technology, in that its emissions and energy performance can be anything on a spectrum from a full battery electric, as Richard just said. If you're actually doing substantially less than 100 kilometers or a bit less than 100 kilometers a day, you may never need to run the range extender. And you are in fact operating in that situation an electric vehicle that just happens to carry a bit of diesel fuel and an engine around with it, but is still, from an emissions point of view, the same as an electric vehicle. Or if you go to the other extreme, if either you never charge it up or you're doing very long daily distances or indeed long distances between recharging, it will tend to morph into looking more like a conventional internal combustion engine powered vehicle, in that all the energy it needs to do that sort of operation will come from the diesel engine, albeit via an electric battery and a drivetrain. So the engine is running as a generator, not as directly driving the wheels. But so anywhere in those extremes is possible, and therefore trying to present one number is to some extent a bit meaningless. So what we've done here is try to present two numbers based on different daily distances or distances between charge, more accurately. One at 150, which is well in line with what the sort of operations the UPS are talking about that Richard's just been talking about. The sorts of distances we'd probably expect this type of technology to be best suited for, where you can spend most of your day in electric mode, but getting a battery big enough to do all of that would be extra weight, extra cost. So you might just want a get back to depot kind of capability from the range extender. But in order to try to test and stress test the technology a bit, we've also then looked at what was a reasonable kind of worst case, as if you're doing up to 250 kilometers a day, probably a bit less in dense urban city type operations, and more kind of interurban type activities on higher speed roads and what have you. As with before, standard sort of test approach. This is on the dyno, so the regen system did work on the dyno this time with this vehicle at 60% payload on the various different cycles, or on one cycle that covers all these different types of operations within it. We have tested though two baseline vehicles for this, not only the original Euro 5 version of the Vario, but in order to fit in with the overall philosophy of the LEF trials, which was to compare each technology against the default alternative new vehicle, and in this case that would be a Euro 6 vehicle. As Richard also mentioned, you can't get a Euro 6 Mercedes Vario. They stopped making them at Euro 5, so we had to we adopted well, what's the nearest equivalent Euro 6 vehicle, Euro 6 diesel vehicle to this, with the similar sorts of payload and cubic capacity, and that's what was tested against, as I say, also the Euro 5. So we have two sets of comparisons to further slightly complicate things, and because the testing on a particular cycle, which I think, if my memory right is about 30 kilometers or so in overall length, actually to generate the sorts of numbers we need for operations at all of these kind of all day at these sorts of operations, a single test of a small little bit of each of those isn't necessarily going to tell us very much, but what it can tell us is exactly what the range extender engine is doing. And it has effectively 4 different modes: off, and then what's called low noise, high efficiency, and high power, depending on how much energy the battery is demanding at any given moment in time. The engine will run slow or fast to get that power. How it does that, of course, and how often it needs to do that depends on the drain on power from the battery, which is dependent on what speed you're doing, what sort of cycle you're in. So all of these issues were used to basically develop a fairly simple spreadsheet model, using all the emissions factors, all the fuel consumption, sort of grams per second emissions or fuel consumption from each of these different modes, knowing what the power output was in each of these different modes, and relating that to how much therefore energy was needed in order to just maintain the battery state of charge. So there was no excess use of the range extender to generate more electricity than the vehicle actually needed, and assuming, as Richard has just alluded to, and in the real world situation, a sort of optimum condition where you use absolutely every available kilowatt hour from the battery, having charged it up fully to start with, and you only use the range extender then to do the minimum it needs to get you back to base, or in this case to complete this one of these two distances. Okay, moving on. The 2 different diesel numbers here in each of these columns refer to the Euro 5 and the Euro 6. In this case, the high fuel consumption comes from the Euro 5 and the lower fuel consumption comes from the Euro 6 vehicle. That's because the Euro 6 vehicle is inherently much lighter than the not unlike a tank structure of the Mercedes Vario. They are built to last, and they do, but inherently that means they do have somewhat higher fuel consumption for the same payload. So these are all at the same standard payload. And these are the figures for the range extender vehicle, this one for 150 kilometres, this one for 250 kilometres, and where the figures here, 14.6 down to 15.2 for fuel consumption, those are the same in each case. That is what the range extender engine will consume on each of these types of duties when it's running. So when the battery has depleted or got to its set point, that's the sort of steady state fuel consumption over the course of while the range extender is running, which doesn't vary, of course, by distance. And this then simply translates that into the equivalent fuel consumption over the trip distance. So in this case, let's say it's got a 110 kilometre range on the long haul cycle. It's doing 40 kilometres at 14.6 litres per 100 kilometres. That means it's over the course of 150. It's consuming 4 litres per 100 kilometres, so about 6 litres over the course of that 40 kilometres at the end where the batteries run out. And this all then just translates that. This is electrical energy from the EV mode. So this is what the range extender then needs to replicate. You're using diesel fuel of the range extender to generate effectively this amount of electricity per kilometre to allow the vehicle to carry on moving in the same way as it did in EV mode. And that all combined together means that at the end of the day, as with the electric vehicle we heard about before, you get a much bigger bang for your buck at the lower speed stuff when the regen work is working particularly well and EV is most efficient. Less of a bang for your buck in the long haul. And particularly it's noticeable in the long haul. For example, the range extender engine is having to work quite a lot of its time in its high power mode, so it's basically thrashing a 1.6 litre diesel engine as hard as it can possibly work. So it ends up actually consuming more fuel than the standard diesel vehicle would, per kilometre in that mode. Obviously, overall, it's only doing that for part of the time because it's in electric mode for a big chunk of the journey. So overall, you still get a big saving, but not as big as you might at the city centre. And clearly, the longer the distance you do per day or between charges, the smaller the savings you'll get because the more of the diesel range extender you'll need to rely on to get you through that trip, which I think is that, and we've assumed an 85% charging efficiency. As I've mentioned, charging efficiency does vary by how you charge and temperatures, and indeed the state of charge of the battery will have an influence on that. We think, and no one's yet contradicted us, that 85% is a reasonable sort of average to use, and that's what's been used in this case. So again, as with the electric vehicles, urban city type operations clearly best for fuel and energy savings here, but saving can still be had even at the higher speeds. This turns that into greenhouse gas emissions, so it's basically the same numbers but turned into well-to-wheel factors using standard factors for electricity and diesel combined. So this is the factor from depleting the whole the battery, which is 74 kilowatt hours, or 0.9 of that. It's got a 10% state of charge at the end. Converting that into DEFRA standard factors, again using grid averages for electricity and standard fuel averages for the diesel fuel. And again, there's a range here because of the two diesel comparators in this case. But the overall percentage savings end up obviously very similar to the energy in the previous graph. And as with the new vehicle, if you assume renewable electricity is used for your 74 kilowatt hour battery charge, but still working on pump average diesel, so we're not applying biodiesel or HVO or anything into this calculation, those savings increase to perhaps 80% in the lower speed cycles. Okay, now the air quality pollutant emissions is where we really highlight the difference between the Euro 5 comparator and the Euro 6 comparator. So as a retrofit of a Euro 5, and if the default alternative was to just keep that Euro 5 vehicle on the road for another 8 years with its Euro 5 engine, then this technology is a very good way of making quite a big step to clean it up. So even when the range extender is running, although it's a bit simplistic, but let's think of it as a Euro 5 car engine is not far off what it is. As a 1.6 litre car engine, it's still much lower NOx even when running than its 4.2 litre, I think Richard said, diesel truck Euro 5 comparator. So you're kind of half, 40 to 50% lower NOx when running, which means over the course of even quite long distances, you still get an average grams per kilometre saving over the course of quite a long trip, 250, and a bigger saving, of course, over the shorter trip. The Achilles heel, though, is, of course, if you then take, well, actually, the comparison should be with the alternative new vehicle, which would be a Euro 6. Then, of course, even a Euro 5 car engine isn't going to match the performance of a Euro 6 truck. So even at quite modest daily distances with quite modest amounts of range extender use, you end up with higher greenhouse gas emissions, NOx emissions from the range extended vehicle than you would have got from a Euro 6 vehicle. That, of course, none of this takes into account the geofencing and the nature of the technology, which allows the range extender to be switched off in city centres, assuming there's enough battery capacity. So this doesn't factor in where these emissions are occurring, and it might well be that having high emissions well outside of a city centre is less bad, clearly, than having smaller emissions in a city centre. But I'll leave that for the philosophers to worry about. So overall, yeah, big savings as a Euro 5 retrofit. If you're going to keep a vehicle for another 5 years or 8 years, this is a good way of cleaning it up in that meantime, rather than replace it completely with a brand new vehicle. Back to Richard.
Yep, thank you very much. There's no way of hiding the fact that the range extender isn't as clean as it needs to be long term. Is anyone else getting lots of echo on this? No, that's gone. Fine. Okay, so what are in-service findings? Let's have a look. If these vehicles had been more mature, if we'd had longer to polish the development and test them before we'd handed them over to UPS, they would have been more reliable. But we were constrained by the timescales of the LEFT project, and we were possibly a little optimistic with how long it would take us to finish the development of these vehicles before we put them into service. So the biggest gripe of UPS and the UPS drivers was the reliability. However, when they were working as they were supposed to work, the drivers loved them. As Brian said, the base Mercedes Vario is a tank, and it feels like it's got the gearbox out of a tank as well. I've been unlucky enough to drive one of the base Mercedes Varios, and after it's done 250,000 miles, trying to find a gear in it is surprising delight. You may as well write it a letter asking for permission to select a gear before even thinking of pressing the clutch. So going from 1,000 shifts a day to none makes a huge difference on the drivers. The MVH is a lot improved, is much improved as well, and also the ability for the trucks to pull out into the traffic. The base Vario has a very, very low first gear, so you're halfway across the junction by the time you're reaching for second, whereas in the all-electric drive version, you just put your foot down and go. I've got to say the vehicles performed pretty much as we expected with regards to EV range. We've been doing this for a while now, so an operational range of around the 100 kilometers is what we were expecting. If you can incentivize your drivers to work at it, you can improve that. So yeah, fuel consumption for the range extender was exactly what we expected. The emissions were unfortunately what we expected. We know that's the area we've got to work at moving forwards. So the barriers to adopting this kind of technology, it's very easy to roll out 1, 2, 3 electric vehicles into a facility, but not 100. You know, if there isn't power there in the first place, getting the DNOs to to upgrade and not charge you an arm and a leg is a problem, which UPS will contest to with their experience at their Camden branch. We try and make it easy by putting chargers in the vehicle, so all you need is an interface box, but this is something that's going to have to be looked at sooner rather than later. Public charging stations for cars are all very well and good, but for back to base trucks, commercial vehicles that are consolidating or trunking in, they need access as and when they need it to charging infrastructure. So through the pilot, we've managed to validate our expectations. We were successful in developing the battery. That's moved forwards from a 74 kilowatt capacity to an 80 kilowatt capacity, and we're using it we're using this battery system in our next evolution of trucks, which are due to go into production imminently. What have we learned? Lots, and that 2 years is not a very long time at all to develop and deliver vehicles. If we were to go for another left style project, I think we would have to ensure that the vehicle was closer to a full production vehicle to begin with, to be able to run the project in the same time period. My issue is if I were to offer everybody on this call today £200,000 and say, go and buy a zero emission capable or all electric HGV, what would you do? There just isn't enough product on the market, and I think that's what we've got to address. So suggestions moving forwards, keep the funding coming. But if you want the product on the market, that funding needs to be for longer with deeper pockets, I'm afraid. Thank you.
That's great. Thank you, Richard. I'm going to move us on because we're running a little bit behind time, but I know Richard and David Thackeray are online, so maybe they can handle questions via the chat specifically, if that's all right, Richard and David.
Yeah, no
and I think we will gallop on because Richard has actually touched on aspects that bring us naturally segueing into the next project, the UPS project joint with Cross River Partnership. And Tom Linton-Smith, I think, Tom, you're with us to give us an overview of the Sewell project.
Yeah, thanks very much, Andy, and thank you, Richard. You've set this up brilliantly because I'm going to talk about the UPS project at the Camden Centre. I'm the substitute today for Peter Harris and Luke Wake at UPS, neither of who can make it. So any technical questions, I'll do my best not to swerve them. Next slide, please. So as you mentioned, Cross River Partnership, we're a partner on the project. UPS were the lead. And as a transport business, they have their series of global goals to reduce their emissions, including 25% of all vehicles to be alternative fuel by the end of this year and 12% reduction in ground emissions by 2025. And as part of their rolling laboratory strategy, they already had experience of deploying battery electric vehicles from their Camden depot, which serves central London. As they expanded that EV fleet, they found that they came up against the barrier of their local electricity supply, which couldn't support them charging additional vehicles at the time they have available, which is overnight. We partnered with them on a previous pan-European project, which involved them upgrading their local supply, which they found to be extremely costly in the hundreds of thousands of pounds as a capex cost for an upgrade, which is essentially to a third party's assets, and a complex landlord arrangement required them to remove the assets were they to leave the site. But this upgrade did allow them to charge up to 65 vehicles. But as that level was approached, because EVs were so appropriate for the kind of operations they needed to run out of there, they found that they were faced with the decision to upgrade their supply again or not. Given the poor business case and the disruption of another upgrade, they were looking for a bespoke solution that minimised disruption, allowed the full 170 vehicle fleet to be electrified and reduced vehicle emissions, and the solution also had to be scalable and future-proof. Next slide, please. So that brings us to the result of this project. which brought together the distribution network operator, which in this case was UK Power Network Services, UK Power Networks, sorry, for the southeast of England, and ourselves at Cross River Partnership with the support of the commercial solutions developer, UK Power Network Services. Next slide, please. So the centrepiece and key area for development in this project was actually the smart charging system, not so much the vehicles, to get round or minimise the need to reinforce the local electricity supply. And one key innovation here was the integration of an on-site energy storage system, so essentially a big battery pack able to provide some additional capacity and resilience, which was supplied by off-grid energy. In terms of the vehicles themselves, though, UPS were already operating a mixture of OEM vehicles produced by Modec until about 2011, and they also had midlife conversions. So this project part funded 20 additional midlife conversions, taking the total number of vehicles to over the threshold that could be simultaneously charged in an uncontrolled way. And then the DNO, UK Power Networks, developed a tool to help them with their timed connection assessment offering. Next slide, please. So the solution then, that's the smart charging solution in a kind of architecture diagram. It's an active network management system controlling the charge delivered to the vehicles. This was combined, as I say, with the on-site battery energy storage to deal with times of peak demand, a key innovation in the project, which we think made it a world first. And so this system now permits charging of all 170 vehicles, and then improved metering and communication between the local substation there and the depot building was also important to support the real-time responsiveness. Next slide, please. So a bit more details on the vehicles then. So UPS converted 20 of its existing diesel delivery trucks to fully electric models. So the converted vehicles are the midlife diesel P80 7.5 ton urban distribution trucks with the Mercedes Vario chassis, drivetrain and UPS bespoke design bodies, the same ones that Richard was talking about earlier, really. So the combustion engine was removed. Typically, it's a Euro 5 4.2 litre diesel engine, and we sent them to A4S, a supplier in Germany. They retrofitted the vehicles with an electric powertrain and batteries. So the converted P80E vehicle has a payload of 3 tons, a cargo volume of 23 cubic meters, and a range capability of approximately 100 kilometers, comfortably exceeding the average daily urban usage. They've got multiple lithium-ion battery packs that are mounted under the cargo floor between the chassis rails, and that provides 21 kilowatt hours of energy storage. They're recharged via an onboard charger with a peak input of 22 kilowatts, and the retrofit meant that they basically didn't have to compromise on their design that they were pretty happy with the walk-in doors that you'll all be sort of familiar with at the back. So the Camden depot, which serves central London, is quite unusually very near to the drop area, so quite different from the Birmingham, Tamworth examples that Richard was referring to earlier. So the actual mileage of these vehicles is quite low, typically sort of between 20 and 60 kilometres a day, most towards the lower end of that. And as a result, we had to stress test the smart charging system using artificial constraints placed on it, as often the state of charge on return to the depot was still quite high. Next slide, please. So in terms of some headlines from the trial period, the vehicles after conversion were on the road for 12 months, and their 65% well-to-wheel reduction in CO2 equivalent emissions allowed us to estimate a 74-ton CO2 saving from the vehicles over the 12 months based on their actual mileage over that time, but with the caveats discussed previously on the comparable figures, although the smart charging system can be programmed to delay charging to truly off-peak periods. And it's also based on a fixed payload, which of course is variable in reality. And I'll hand over now to Brian for a bit more detail on the vehicle testing.
Okay, thanks, Dom. Yes, so much more simple this time around. Same, because it's the UPS project, and we had 2 projects involving UPS, both this one and the Tether project Richard was just describing. That's allowed us to have apply 2 baseline vehicles. So again, the Euro 5 original Mercedes Vario and a Euro 6 closest equivalent. 85% charging efficiency again assumed, and dyno testing at 6% payload across the standard cycles. So here again, these are the same figures as we saw with the tether for the diesels, the Euro 6 and the Euro 5. And these are the energy consumptions here. Just obviously electricity, there's no diesel fuel this time around. It's not a range extender, just the electricity. And this is grid metered electricity, as it were. This would be the electricity as you would pay for from your electricity bill, because it takes into account the charging efficiency. So it's not just the onboard electricity consumed; it's the metered consumed. And as with the smaller battery electric van we heard about from Newton Menzies earlier on, and Philippa, substantial energy savings, which increase, of course, as speed reduces. So in the sort of city centre operation that the UPS Camden depot is talking about, kind of 70% or so savings are readily achievable. City urban best for these vehicles. Converting that into greenhouse gas emissions, similar sorts of percentages, again using standard factors. And again, if we then assume, rather than the standard grid average factor, we use a 100% renewable tariff. So we know that all the electricity consumed comes from renewable sources. Then those savings increase to well over 90%, regardless of cycle. But again, obviously the biggest savings at lower speeds. And air quality is very simple, because there isn't any pollutant emissions from the exhaust. There is no exhaust on this vehicle. We don't factor in obviously other emissions from power generation. We're assumed that if there is emissions from power generation, that's not in city centres. It's going to be outside. So the particulates and NOx emissions from that are less of an issue, because they're not in urban densely populated areas. So we only look at tailpipe for pollutant emissions, and this really shows the difference between the Euro 5 and the Euro 6 in terms of the typically 80%, 90% reductions in NOx emissions just from going from Euro 5 to Euro 6. But of course, battery electric goes even further, goes to 0. And back to Tom. Sorry, I missed. You skipped over one of your earlier slides. Did you want to talk briefly about that one, Tom?
No, that's fine. I think okay. I covered it.
It'll be in the pack anyway, if anyone wants to refer to that. Right.
Oh, sorry, I missed that. I do want to cover that again. I just go back to that.
Sorry for anyone feeling seasick at this moment. Right.
So yeah, just touching again on the smart charging. Because this part of the project was really successful. As I say, it's sort of one of the key innovations, because UPS already had some experience with the vehicle conversions. Yeah, it was a key innovation, really successful. It delivered enough charging time for more vehicles at the site, should they choose to expand in the future. So the target was 170, but there's capacity now for up to 210 vehicles. And it really helped prove the business case of this kind of scalable solution if you implement smart charging first and then go for the grid upgrade later if you really need it. But this part of the project was actually cost neutral compared to a conventional upgrade. It was still quite expensive, of course. It was partially funded, but this included significant development and other costs which would reduce in future deployments. And if it were to be installed now, it would deliver around a 69% saving compared to a conventional upgrade. And with the conventional upgrades, there's a huge variance in the cost that they can come from the DNO. There's all sorts of regulations around the kind of cost, and it's basically depending on how close you are to the nearest substation and how much spare capacity there is. Using this system can deliver additional savings as well by prioritising or delaying charging to certain times of day, including maximising the use of nighttime electricity tariffs. It helps if you've got a good telematics system which can tell you state of charge and communicate with the charger quite successfully. We had a few issues with that, but at the Camden site we worked out we could deliver about 10% energy cost savings through maximising on the nighttime charging. So yeah, on to the next slide. As I say, the solution is pretty scalable, can help avoid regret costs, and operationally there's some reduced fuel cost and consistently good feedback from the drivers. However, in terms of charge point and cable management, this was a key unexpected cost as the equipment is prone to being damaged in the busy Camden depot. We looked at a range of different options for overcoming this and have so far settled on overhead retractable cables for charging. In future depots, there would be consideration of a bus bar or a robotic arm charging solution, which takes out some of the driver interference. We researched that as part of this, and we also looked at wireless, but that's perhaps a longer term solution as the efficiency is just not there yet. So whilst the smart charging is the central part of the project, we also have the vehicles, of course, and UK Power Networks developed their timed connection offer, basically automating an assessment tool to speed up the process of offering timed connections, which used to take a number of days to do the assessment. It now takes hours. So at one London bus depot during the project, they used this tool to offer a connection for electrifying a bus depot, which would reduce connection costs by 82%. And it's now been integrated into their distribution network planning toolkit and demonstrated to other DNOs. I've seen there's a few questions coming in about flexible energy, community energy, and sharing the capacity. So we've since started exploring further revenue generation, and that potential can help improve the business case for fleet electrification by accessing electricity flexibility markets when there's predicted to be spare capacity, and treating the vehicles as energy assets, as well as incorporating local renewables, so incorporating solar PV, and also private wire connections such as publicly accessible rapid chargers outside the site. We're doing this through a recently launched project with some support from the Industrial Strategy Prospering from the Energy Revolution Challenge via Innovate UK again, and this wouldn't really have been possible without the building blocks of the SOL project and the funding through the LEFT programme. So it really is a sort of a building blocks project that's allowed us to take this further. We're doing that with Moixa, UK Power Network Services, UPS, and ourselves. Moixa have an AI platform which predicts expected demand in the depot and can make more available for other users. Next slide, please. So I'll end on vehicles and vehicle availability. One of the main challenges we had in the project was the vehicle conversions. The conversion process was costly. We weren't able to procure what we wanted in the UK. As I mentioned, that went to A4S in Germany, and difficulties with the supplier caused some delays to starting the monitoring period. We had to seek a project extension to do the full 12 months of in-service trial. In the medium term, the available stock of appropriate ICE vehicles for conversion is depleting as well. As was mentioned before, the Mercedes Varios are no longer produced. So one of UPS's solutions to this is to invest in new OEM vehicles. Things have moved on quite some way since 2016, of course, when this project was planned, although the EV segment for larger vans is still not mass market, as Richard mentioned previously. And late last year, UPS announced their significant investment in UK manufacturer Arrival on their EV van platform, which gives an idea of where they're headed with that. So I'm sure they're hoping to see many more of those vehicles on the road quite soon. And that is where I'll leave it.
Brilliant. Thanks very much indeed, Tom. Any quick questions for Tom that we can't handle via the chat, because we're going to have to move on, given the, I think Ian, was that Ian? Yeah.
Yeah, Tom, just a quick question for you. In your opinion, could you make this commercially work with the existing market mechanisms around for valuing flexibility on charging?
I think so, yes. I'm not an expert on that, but well, that's what we're trying to prove at the moment, really. That we do think it will work commercially, integrating into Moixa's grid share system that I talked about in our new project. And there is some discussion I know around whether the flexibility markets will continue to offer the returns that they do currently. and we want to try and do it in as real time as possible to maximise the benefits from that, rather than bidding ahead of time. So that's why we want to try and use this AI platform that can factor in hundreds of different variables at the same time, rather than sort of pre-selling capacity that you can guarantee is available. Hope that answers to an extent.
That's great. Thanks very much indeed, Tom. Hopefully you're online for a few more minutes. If there are any questions, we can handle via the chat. I'm just conscious of time, so we want to sort of, if you like, bring this all together. We've had 4 presentations from the 4 projects that outline what's happened over the last 3 years of the LEF programme. And I think just in terms of next steps, LowCVP will be bringing this together with the other 4 projects that were reported last week and summarising this, both the testing and the project experience, into a public-facing report, a nice, simple and accessible public-facing report of the key outputs. That'll be hopefully published in the September timeframe. So we're gathering up any views from the project and indeed from other stakeholders to feed into that report. Some of the headlines that we're taking away from this, and we're trying to find a way of articulating this, is that there are clearly a range of technologies out there at a range of different places on the technology readiness levels. But increasingly, we're seeing the OEMs coming out with some of these more advanced technologies, both full electric vehicles, hybrids. We now have a range extended hybrid from Ford in the Transit size. So there are more and more of these things being picked up and run with at production scale and production levels. What we've tried to do is to capture these into sort of groupings that we can highlight how we might move forward from a policy perspective in supporting the DfT in their decarbonisation plans. And as I mentioned at the start, we've sort of categorised the evolution technologies within which we put the KERS trailers that will give us some savings, but they're not going to give us 100% reduction in tailpipe emissions. But they're certainly there, and potentially with the development, they could support us in our trajectory to reduce the carbon impact from vehicles, be they existing vehicles or indeed new vehicles. Some of the transition technologies which can make quite a step change, and particularly when combined with low carbon fuels in a gas truck that we saw in the long haul applications, for example. Or the range extenders, which clearly have an opportunity here to give us zero emissions in city, but not compromise any of the long haul activity and the longer ranges needed in a number of commercial vehicle applications. One of the challenges is, of course, that you can't actually always have the right vehicle for every job, because they need to do all jobs, and it's quite a challenge trying to find the optimum vehicles. And then we have the revolution technologies, within which we put the battery electric vans and HGVs, which are clearly showing that very, very significant step change. And they're the zero emissions, if you like. The ultimate target for DfT is undoubtedly a net zero emission fleet, and that's a legal requirement now in 2050. So we have to be looking to how we progress towards that as we move forward. In terms of the activity, I'll just step through the next couple of slides. I think it's worth just taking from TRL, TRL drew together some of the key operational data and also ran the monitoring of the trials. And I think there's some learnings there in terms of how we would run future programs. So Marcus, if you're on, maybe you can just run through these last couple of slides on TRL's views of how this has gone as an overall program.
Hi, thank you, Andy, and thank you to all the projects. Andy, can you just confirm that you can hear me?
Yeah, we can hear you.
Yeah,
yep.
Great, thank you. So first of all, we've pulled together sort of overall successes, so rather than making them specific to individual projects, but a very clear message that comes across here is the very large energy savings we get from electric vehicles, particularly in urban areas, and that was consistent across all the different projects and consistent between the control trials and the fleet trials. One thing we did note was the importance of cabin heating as a significant demand for energy, particularly with the delivery vehicles and the way that they're used, with the doors open a lot and the open structure. So there's probably an opportunity to improve and optimize how heating works to get further energy savings. In addition to the obvious energy and emission benefits of EVs, we note a lot of benefits in terms of driver satisfaction, and also your depot. You're not having exhaust in your depots, the vehicles are cleaner, and more broadly, the customers are seeing a modern, very clean, very quiet vehicle. From the trials, because we were able to bring together results from the controlled laboratory type trials and in-service trials, this was very successful, because it meant that all the different duty cycles could be considered, and that where there were difficulties with the operational trials, we had the controlled data to help interpret them, and also to fill in gaps that couldn't be met in the operational trials. So that was a very successful part of the way that the trials were operated. And as a message that's come across from a number of the projects has been that actually the data and the experience of having to conduct these trials has helped optimize and develop the technologies, focusing more clearly on the most efficient duties, and the trip lengths that we get the greatest emission benefits from. The lessons from all of this will help inform the design of future trial programs. One thing that we as the monitoring contractor are very conscious of is one size didn't fit all. There was initially, the idea was that very standardized methods would be applied to data collection and analysis. And in fact, in practice, we note that the different technologies were at different technology readiness levels. There was different trial objectives for different projects. So we note the work that Newt were doing on improving the utilization of the vehicles, as well as just the comparison against diesel, the smart charging work that the UPS project was doing, that weren't necessarily properly reflected in the standardized comparisons that we've made based on energy consumption. So for future trials, we'd very much recommend that you have project-specific indicators, and that you define the data collection and analysis requirements that are very much linked to the technology, and that does need to be defined at the funding stage and not subsequently. And this means that we also need to look at more sophisticated analysis techniques. There was indeed one of the presentations in the previous session on long-haul vehicles was showing how Cambridge University have done some more sophisticated analysis that enables better account to be able to be taken of how loading and speed can affect energy consumption. This does require very strict use of telematics data. And we need to make sure that the telematics data are validated, as this was one of the practical problems that we had with these trials. Also, and I think this has been picked up in one or two of the previous presentations, particularly given the different technology readiness levels of the different vehicles that we used, a phased or staged approach may be more appropriate, so that we validate the operation and validate the data collection mechanisms before you undertake full fleet monitoring. An early stage in those phases would be to hold the control trials, because that helps to not only to demonstrate that the vehicles are operational as intended, also to validate the telematic system. And once you've got better data on the scale of impacts on energy consumption, you can design your sampling methodology better so you understand what sample size do you require to detect a change of a given range of percentages. Clearly, a number of the projects had problems with baseline and data collection. So, a future program does need to make sure that there is very strict control a baseline vehicle that it's chosen, and that we do have true comparability of operations and loadings. One area that I think we would like to have done better and done more of would have been to have had more ongoing exchange between between us and the projects, and indeed amongst the different trial stakeholders for sharing experience and progress as things were going on. Part of the reason that didn't work so well was because there were various delays in getting the data. So in the end, we ended up being more focused on trying to manage the different data sources than in engaging with the stakeholders. So we would strongly recommend that there's more opportunity for those sort of activities in a future program. So thank you for that, Andy. And yeah, I'll call it there.
Thanks very much, Marcus. I would say one other thing that has definitely come through from this and the previous seminar was the point about on the engagement that we have to make between the energy system and the vehicles. Commercial vehicles are complex and their operations are very complex, but vehicles don't create any carbon. It's the fuel from which all the carbon comes. So engagement with the fuels is absolutely critical in any work that we're going to do going forward. I'm going to flag up this one slide that Brian's just showing up. There's potentially quite an interesting seminar going on the 1st of September. Again, we'll make this available, but the Transport Decarbonisation Alliance are looking at some of the opportunities for potentially long-term zero-emission trucks and things. And we'll also flag up our last slide, which has got mine and Brian's email addresses on it. But we will leave this open, and we'll continue to run this if there are any comments, thoughts back from the floor. Apologies that we've run right up against the nominal end time. So those that do have to go, please, thank you very much for your attendance. But we're happy to sit and answer any questions, take any comments for the next half hour or so from anyone who wishes to remain and actually join us to discuss that. So any thoughts or comments, if you can raise hands, and we can then flag up to any people. But any comments you'd like, email into myself and Brian, and we will take those forward in our thinking about the dissemination activity. Any comments at all? Questions?